Good morning, everyone. Thank you for coming. We are very excited to have at our CS seminar today Tim Rudner, who is a faculty fellow at NYU's Center for Data Science and an AI fellow at Georgetown University Center for Security and Emerging Technology. The goal of Tim's research is to create robust and transparent machine learning models, and he'll be talking to us a bunch about that today. He holds a PhD from Oxford, as well as a master's degree from Oxford and an undergraduate degree from Yale. And sort of notably, the disciplines involved there are statistics, mathematics, economics, probabilistic machine learning. So lots of sort of multidisciplinarity brought in there. And he was selected in 2024 as a rising star in generative AI and is also a Qualcomm Innovation Fellow and a Rhodes Scholar. And we're really happy to have him with us today.
Thank you so much for the kind introduction. I'm super excited to be here. And as Rebecca said, I will be talking about my work on probabilistic methods for robust and transparent machine learning. All right, here we go. All right, so as some of you may be aware, sepsis is a severe immune response to infection that kills almost 300,000 people per year in the United States alone. So naturally, being able to make a dent in identifying sepsis early could save possibly thousands of lives. And this is exactly what the goal of an effort by Epic, a medical software company, was, which developed a system to identify sepsis in hospital patients early. And that system was based on a machine learning model that was trained on data that was gathered across hospitals in the United States. And so this was a model that was trained on data from a small number of hospitals and then was rolled out across over 100 hospitals nationwide. And as also many of you might know, shortly after deployment, it became clear that the system, in fact, did not work as intended. Crucially, it failed to spot many cases of sepsis and was pulled from deployment shortly after it was rolled out. And of course, this is just one of the many examples of machine learning systems being deployed in safety-critical settings where they didn't actually work as intended. Another example is a system that was developed and deployed by Google Health. This is a system that was developed to diagnose diabetic retinopathy, which is a medical condition caused by diabetes and can lead to loss of eyesight. And this model was developed based on data collected in the United States and rolled out in Thailand. And there were some regulatory reasons for why that was done. And here too, why it was rolled out in Thailand specifically. And here too, the model did not in fact work as intended. And instead of speeding up ophthalmologists' work and leading to faster diagnosis, more effective diagnosis of patients, it ended up working poorly, leading to a backlog because there was so much human supervision involved because the model was poorly calibrated. And this system too was pulled shortly after deployment. And of course, as we think about the ways in which machine learning models are deployed at scale, we need to think about ways in which machine learning models might not just cause individual harm, but also exacerbate existing societal, racial, socioeconomic disparities when we do so. And there are various examples of that already having happened. And those examples, of course, well documented both in research as well as in the news. And the common thread across the different examples that I just gave you is that it is currently a fact of life that machine learning systems often fail when they're exposed to unexpected conditions upon deployment. And that issue brings me to the fundamental goal of my research, which is to create machine learning models that we can trust, and to do so by developing methods that improve specifically model robustness as well as their transparency, so that we know what they do and specifically focusing on aspects of fairness. So briefly, before I talk about some of the technical contributions that I've made to tackle this research goal, just a few words about my background. Don't want to linger on this too much. Rick already gave such a kind introduction. So I studied at Yale. Oxford was fortunate to be funded by Rhodes Scholarship. And since 2019, I've worked as an AI fellow at Georgetown University at the Center for Security and Emerging Technology, where I've been engaging in AI policy. I've written a number of papers that specifically expose policymakers and non-technical audiences to critical questions in AI safety. And I like to point out that I did this before it was cool to do that, before there was a lot of attention here. And I'm so happy that there's a lot of attention on AI governance and AI policy now. The way I view my work is really to provide technical solutions and also think about policy mechanisms that can allow us to have robust and transparent models that we can trust. And currently, I'm a faculty fellow at NYU, and one of the really wonderful things about that position is that I've been able to teach. So this is my third year at NYU, and I've been able to teach one course per year. I feel very passionate about teaching and mentoring. Kind of the way I think about teaching and mentoring is that really I want to educate future leaders in research and society. So I think about teaching and mentoring kind of in a general sense as both, of course, kind of with the research students that I work with and trying to growing and educating future researchers who can push the field forward and a way for this work to kind of have a multiplier effect through my students, but also, of course, just as a teacher, I know that many students do not pursue research, and it's my goal to be able to educate students in a way such that they can be responsible, users, consumers, and shapers of machine learning technology, whether they do so in research or in other roles in society. And kind of one crucial part of my teaching philosophy is really to teach students, both research students and students in the classroom, to ask the right questions. So one, to just ask questions in general. So, you've all heard the saying, there are no stupid questions. I really generally believe this, but, it continues to be my mission.
Sorry?
Make students.
Okay, no problem.
Sorry, is there a question? Maybe not. Okay. Audio glitch. I think with research students in particular, kind of one of the key goals that I have in working with and mentoring students is to really teach them how to ask the right questions. Then we can think about how to answer them. So now, so much about my background. With that, I want to return to the topic of this talk, and I want to focus on two different vignettes of my research. First, I'm going to talk about how we can improve robustness of machine learning models with a specific focus on designing machine learning models and training them. And specifically, I will show how to create trustworthy models with what I call data-driven domain-informed priors. And then the second part of the talk, I will be talking about how to improve the transparency of models that are already trained and are ready for deployment. And here too, I'll be using probabilistic methods. In this case, to interpret pre-trained models, pre-trained vision language models, and specifically trying to understand what concepts they might, quote unquote, know and understand. So given that probabilistic models are crucial to my work, I think it's useful to just maybe take a moment and spell out what I mean by probabilistic models. So first of all, the key hypothesis of much of my work is that probabilistic modeling can help us understand model failures and improve model trustworthiness. And what I mean by probabilistic modeling in a somewhat simplified way is that if we have, let's say, a supervised learning problem with inputs X and corresponding labels Y, and we're interested in some quantity, for example, model parameters, theta, the first step is to specify a probabilistic model over our labels given the inputs, as well as a prior over the parameters. So the terms that we typically use for the first term is the likelihood of the model. And over here, we have a prior belief over the quantity of interest, for example, the model parameters. Second, typically in probabilistic modeling, we try to find a posterior of the quantity of interest given the data that we've observed. In practice, this is often difficult, and we resort to approximate methods to do this in model classes that are too complicated and make computing this posterior intractable. In this talk, I will mostly focus on this first part, on building better probabilistic models, specifically building better priors and to make models more trustworthy. And so this is the rough talk outline. Like I said, First, I'm going to talk about design and training, and then I'm going to talk about model deployment. I'll start with the first part, specifically trying to answer the question, how can we create trustworthy neural networks with domain-informed, data-driven priors? And this is based on a few different works that were published over the last few years at NeurIPS and ICML and AI Stats. Okay, so the key question that I try to answer with this line of work is, how can we encode beliefs about desirable model properties that help us improve the trustworthiness of a model into training? No. There seems to be, for those joining on link, a fire alarm. Oh, okay. So it should stop any moment. You keep going. I go back. All right. Please excuse if I'm not quite as cordial while this is going on, but I'm trying my best. Okay. All right. So what I'm going to do is if you take a probabilistic approach, Fantastic.
We continue.
No worries at all. All right, so we're back. I'll just repeat what I just said on the previous slide. So the key question that I asked kind of with this line of research is, how can we encode beliefs about desirable model properties that improve trustworthiness into neural network training? And when we approached this was through a probabilistic approach, of course. Specifically, I'm going to read this out because it's a mouthful. The goal was to find a prior distribution over neural network parameters that places high probability density on parameter values that induce functions with desirable properties. Now, we need to think about what these desirable properties are, but in principle, that's what we're trying to do. The fire alarm just started again.
No, where they say.
I see. All is good. Okay, fantastic.
I'll also just cover it.
Okay. All right. So, and what this means is that we will place a prior distribution. Thank you so much. Over the neural network parameters, and we want to place a prior distribution that favors neural networks with desirable properties. I'm going to talk about some of these desirable properties in a few slides. But first of all, what do I mean by data-driven priors? So specifically, what I mean is that we have a prior distribution over the neural network parameters that's conditioned on some useful context information. And this context data I will denote by using the subscript C going forward. And specifically, we assume that we are working on a problem where we have some useful information about the problem itself, because maybe we've spoken to a domain expert and would like to incorporate that into the learning problem, and specifically to design a prior that favors certain solutions. Now, importantly, this context data is assumed to be different from the training data. So the training data might be, for example, labels, and we might want to solve a classification problem. This context data might be separate, or will be separate from this data. And specifically, the context data might give us information about what data points we would want the model to be more uncertain, or have higher predictive uncertainty on. And so to get a better sense of what this data-driven prior actually is, we can use Bayes' theorem in order to express this conditional distribution in terms of other distributions that we can reason over. Specifically, the data-driven prior can be expressed by Bayes' theorem in terms of what I refer to as a context likelihood function, a base prior, and a marginal likelihood. So this base prior, we will ignore for most of this talk and just assume that the base prior is just a simple uninformative distribution, something like a Gaussian or Laplace distribution. I'd be happy to take questions about that choice later on, but this is a practical choice because we know that this works well in practice, given what algorithm we will get out of this approach at the very end. And so then that raises the question how to specify the context likelihood and possibly how to compute this expression. And unfortunately, the marginal likelihood, the quantity at in the denominator here, is actually intractable. Hence, we can't actually compute this data-driven prior, right? Conceptually, I'm saying like, this is something that we want. We want a prior that's conditioned on useful information. We can express it this way, but we can't actually compute it, which is a challenge. which then raises the question, can we somehow avoid this intractability? And to answer this question, I want to briefly digress and talk about training machine learning models with standard uninformative priors. And to do this, I'm going to refer to a kind of a set of approaches that I would broadly describe as Bayesian inference as optimization. And there's an announcement. Just 1 second. All right. Fire drill is over. All right. So in approaches that in machine learning approaches that are statistical approaches that approach computing some notion of a posterior or conditional distribution via optimization, we have a simple kind of approach to do this, consisting of minimizing some loss and then having a specific type of regularizer added on to that loss. And this regularizer, importantly, is typically expressed in terms of the log unnormalized density of the prior. So this is very important because standard approaches that approach Bayesian inference as optimization do not actually require us to have access to the unnormalized prior, but instead only require access to the log density of the unnormalized prior, which I'm denoting by p tilde over here. I'll briefly mention this function h over here. So h could be the identity function in some approaches, or it could be, for example, the KL divergence in other approaches. But this is a general expression for approaches that try to solve Bayesian inference as optimization. And importantly, as I said, this only requires an unnormalized prior density. And approaches that fall into this category are, for example, variational inference, stochastic gradient dynamics, Hamiltonian Monte Carlo, as well as maximum a posteriori estimation, just to name a few. And so if you're familiar with some of these methods, you might recognize this. If not, don't worry, because we're going to focus on maximum a posteriori estimation, which is a very simple approach, which tries to find the mode under the posterior distribution, as opposed to the full posterior distribution itself. So in other words, the mode, of course, are the most likely parameters and most likely values under the posterior distribution. And we are going to look at maximum a posteriori estimation, because under that, this simplifies, and the function h here is just the identity, and we end up with a simple term that consists of a loss that we try to minimize and a log of an unnormalized prior density estimation. And if we have a very simple prior, for example, an uninformative isotropic Gaussian prior, this ends up being a loss with an L2 penalty on the model parameters. So something that we do, that we use every day in training machine learning models like neural networks. And so the process here is just super simple. If we want to perform this kind of estimation, all we need to do is compute the gradients with respect to the loss with respect to the parameters, as well as the gradients with respect to the log unnormalized prior density, and then update our parameters with simple gradient descent. So this is a very simple mechanism. We do this all the time in machine learning when we optimize neural networks. Now that we know that we can frame Bayesian inference as optimization using this simple recipe, what about data-driven priors? How can we use this insight in order to actually make use of data-driven priors the way I described them on the previous page? And well, the answer is, let's just replace the components that we had here that involve the unnormalized, the log of the unnormalized prior density, and include this conditioning on our context data. Looking at this, we immediately recognize that, wow, of course, this is only the log unnormalized data prior, which consists of the following terms: the log context likelihood, as well as the log base prior. And the log marginal likelihood disappears from this expression. In other words, the part that I told you on the previous slide that makes computing the normalized data-driven prior density intractable disappears from the optimization objective. So the part that makes the data-driven prior difficult to use does not actually show up in optimization methods that use this prior. Which then brings us to the next part. Now that we know how we can use these priors, how do we actually construct the priors by constructing a suitable context likelihood? Because that's the only component that's missing at this point in order to make use of these priors. And I'm going to focus on two different types of domain-informed priors. And first, I'm going to talk about domain-informed priors that allow us to achieve more reliable uncertainty quantification in neural networks. And to do that, I'm going to come back to the problem that I started with, that Google Health tackled, which is diabetic retinopathy detection, where the task is to detect diabetic retinopathy from patients' retina scans. And this involves using a retina scan, putting it through a neural network, in our case, a probabilistic model, making a prediction, then getting a diagnosis out of this. Now, this is not a particularly safe pipeline. So instead, in order to account for the model's uncertainty, for example, the model is highly uncertain, maybe we don't want to trust it, we can use a pipeline called selective prediction. Selective prediction involves not just creating a prediction, but also getting a corresponding uncertainty estimate with that prediction. And if that uncertainty estimate is above a certain threshold, we refer this data point for expert review. If it's below a threshold, we use the model to perform automated diagnosis. And of course, this requires us to have uncertainty estimates that are actually reliable. So in other words, whenever the model is actually out of its depth, it should raise its hand and say, my uncertainty about this prediction is high, which we can then act on by bringing essentially the human into this prediction loop. Now, in order to approach this problem, we actually tried to simulate the kind of distribution shift that Google encountered when they deployed their model in Thailand. And the way we did this is we used the same training data that they use, and specifically this is training data that was gathered in the United States, and this is the IPAX data set, and it contains retina scans with labels going from showing no signs of diabetic retinopathy all the way to showing proliferative signs of diabetic retinopathy. This is the data that we use for training. In order to simulate the distribution shift that Google encountered when deploying their model, we used data that was gathered in data. This is the APTOS data set. This data set was gathered, of course, from a different patient population, and it was also gathered using different measurement instruments. So these measurement instruments were actually more advanced than the measurement instruments that were used in the United States. But using different measurement instruments might result in the appearance of the retina scans to differ somewhat and potentially meaningfully in this data set compared to the data set in the US. There are many distribution shifts that occur here. You can see that there is a class shift over here, and there's also a covariate shift, meaning that the retina scans look differently based on this different patient population and the different measurement instruments. In our example, we binarized these data points to be either exhibiting no or mild diabetic retinopathy or moderate or worse. And then we tried to solve this binary prediction problem. We trained a model on the data gathered in the United States and then evaluated it under the data that was gathered under distribution shift in India. So how can we now use the ideas that I presented before about how to construct data-driven priors to train models that exhibit reliable uncertainty quantification and allow us to use the selective prediction pipeline for diabetic retinopathy detection? And so, well, of course, the goal would be to somehow design a prior distribution that favors parameters that induce functions with high uncertainty under the distribution shift, so that whenever there's a data point that is meaningfully different from the training data, the model can raise the alarm and say, I'm uncertain here, or more uncertain than on the training data, and then we can refer this data point to an expert. Now, of course, we don't actually know the distribution shift a priori, right? We don't know this shift before deployment. So what we do is we try to work with experts in order to specify a slightly different goal, which is to instead specify a prior distribution that induces functions with high uncertainty on some context data that we think might somehow emulate the kind of distribution shift that we might observe at deployment. And this will be imperfect, but we can try our best to think about the problem, working with domain experts to do as well as possible, and hope that by having more reliable uncertainty on the context data, we also have more reliable uncertainty on the data that we see at deployment. Now, this visualization here is quite extreme, where you see the context data and the distribution shifted data being separate, right? But of course, in practice, these are complex data spaces, and there's probably like a significant amount of overlap. Okay, so how can we actually design uncertainty-aware priors? So the goal here is to get more calibrated predictions under distribution shifts. Where calibrated just means that we want predictions that have where the uncertainty matches the chance of the model making a wrong or right prediction. So if the uncertainty is high, we want the model to actually be more likely to make a wrong prediction. If the uncertainty is low, we want the model actually to make a correct prediction. And so here I'm just restating the expression of the logarithm of the unnormalized prior density that we looked at on the previous slide. I already told you the base, that for the base prior, we're just going to assume some simple distribution. So now all we need to do is we need to think about how to specify this context likelihood and how to specify the context data. So let's look at the context data first. For context data, we first spoke to domain experts and talked to them about what kinds of issues we might encounter under distribution shifts. And well, of course, like I said, we might not know the exact distribution shift that we encounter. We were told that we might observe certain types of visual distortions or visual artifacts with different measurement instruments, and that we could try to simulate these kinds of distortions with corruptions to our image inputs. So as our context inputs, XC hat over here, I'm sorry, this should not have a hat. This is just the same XC as up here. We constructed highly corrupted retina scans based on conversations with the IPAX team in the US, who told us what possible distortions could look like blurring and potential like visual artifacts showing up on the lenses. And then we matched those highly corrupted retina scans. Again, this should not have a hat. I apologize for that. We matched these highly corrupted retina scans with random labels in order to kind of tell the model that these highly corrupted data points might have either of the two classes of, mild or no diabetic retinopathy or moderate or worse. And then the way we use this data was by constructing a context likelihood, in this case, using a Gaussian distribution, where our model predictions, just shown, bless you, as the outputs of this function f over here, where f denotes our neural network, is supposed to match the random labels that we see over here. And I'll briefly note that over here you see a covariance term. This you can think of as a hyperparameter. In the simplest case, this is just a diagonal covariance, but we found that if we use a covariance term that reflects meaningful distance in prediction space, that we can improve the performance, and specifically, this can vary how smooth of a function our prior favors. But the focus here is on essentially trying to get predictions that match these random labels. Pretty simple, right? And this is one example of specifying a context likelihood. There are many other different approaches you could specify this to get a similar result. But here I'm focusing on this because if the model has a high log density under this context likelihood, this means that the model successfully exhibits high uncertainty on our context inputs, which is what we wanted, all right? So now the question is, does this actually deliver what we want from a model? Meaning that, does this actually improve the reliability of the uncertainty quantification under the actual distribution shift we encounter at deployment? And so to find that out, we looked at the area under the RC curve for this binary prediction problem for our selective prediction pipeline that I showed you before. So what does this look like? This means that we look at a few different settings. First, we look at the setting where we don't use selective prediction at all. We just use our evaluation data set and perform binary classification, and then look at the area in the RC curve without referring any points to an expert. Then we also look at the performance if we refer 50% of points to an expert, and we only look at the performance, that's what I'm going to report here, on the 50% of points that we did not refer to an expert, meaning the points that the model chose that it was sufficiently confident on. Then lastly, we also look at the more extreme case where the model only is evaluated on the 30% of points where it's most confident. All right, that's the setup. Now let's take a look at what happens with the state-of-the-art model. And this model is based on the winning technique in the Kaggle challenge, where the IPACS, the training data set, was first used. And as you can see here, we see a very interesting pattern. So if we don't refer any data to for expert referral, so only evaluate the ORAC, evaluate the ORAC on the full data set, we get an ORAC of like 92.2%. However, as we refer more data points, instead of the model exhibiting a better ORAC, it's worse, right? Meaning that the model is overconfident and wrong, which is absolutely terrible. If you want to rely on the model's uncertainty, that's exactly what you don't want to see. You don't want the model to refer the wrong points to an expert. And in fact, this is actually exactly what happened when Google Health deployed the model in Thailand, which was that the wrong points were referred for expert review, and the points that weren't referred for expert review were often misclassified. So this is terrible. Let's see whether we can do any better using the simple data-driven prior that I showed you on the previous slide, that's just based on domain knowledge about what kinds of corruptions we might observe. So this is the performance that we saw here. And as you can see, we see a significant increase across the board, right? You see in each of these scenarios, we see an improvement, even in the scenario where we don't actually refer any data points, also suggesting that this kind of regularization might generally be useful to improve performance. And we see this, I've seen this across a few different papers. And we have some like interesting empirical results here. I'd be happy to take questions about that too, if anyone is interested. But what I want to highlight here is that these results are both a success story and a bit of a failure. Because as you see, the improvements in terms of the number of percentage points that we improve for the area under the RC curve are significant, but they're still bad, right? Any decrease in this performance means that the model's uncertainty actually performs worse than a random sample, which of course is absolutely not what we want, right? So this just kind of highlights that this is a really challenging question, a really challenging prediction problem, and kind of noticing that, I worked with folks at Google on a paper that we presented at NeurIPS 2021, where we open source all of our code, we open source all of our pre-trained models, and establish this as a benchmark in the uncertainty quantification, especially the Bayesian deep learning community. And this remains a really hard problem. And up until today, this was, of course, 3 years ago, we haven't been able to make more of a dent than what I'm showing on this slide over here. But this continues to be ongoing work, and I also continue to work on this. And there might be interesting directions, essentially, especially combining the kinds of uncertainty quantification that we pursue here using a Bayesian approach with other methods that are pursued in the community. I just want to point out very briefly, one ancillary result that we had here was that in a follow-up paper to this, we looked at the extent to which having foundation models pre-trained on billions of images might actually be able to perform better than what we were able to see here. And we found that, in fact, in a big benchmarking study that we also did with Google, while pre-training a foundation vision model on billions of data points resulted in an improvement in performance across a wide array of tasks that were based on model's uncertainty. This is the one task where, in fact, this did not help. And actually, the pre-trained model performed less well than the best model trained on scratch, which was this one over here. So this remains a challenging and open problem, and I'm excited to know about evaluation and benchmarking as an important area of research. So with this, I want to move on to my other work on specifying domain-informed data-driven priors for group robustness and fairness. I want to pause here very briefly. So I'm currently, based on my own timer, at 30 minutes. I think I'm good with time, but based on when do we need to leave this space, how much time do we have?
this space.
Right.
So it's ours as much as it's ours. I think we should continue, as you would have
Good.
already to give them some note on the Zoom that we plan to do that.
Okay.
If people need to leave, they can leave, of course,
Yeah.
and we will ultimately post the recording on our Barnard CS YouTube channel if people have to leave. So it's
Fantastic.
heroic so far. Please
Thank you.
continue and, take, give us the talk that you intended to give.
Sounds good. Thanks, Rebecca. All right, so let's talk about how we can design domain-informed data-driven priors for group robustness and fairness. And this paper was presented at ASS this year and was awarded a notable paper award. So group robustness is a setting where we would like for our model to generate fair predictions, meaning in the context of group robustness, to perform well across groups, meaning to achieve, for example, a high level of accuracy across different groups represented in the data, meaning that we want the model to perform well on groups that might be plentiful in our data sets, as well as on groups that might be underrepresented in our data set. And so, for example, we might have a vision data set that contains a large number of images of white people and a smaller amount of images of people of color. And we want to ensure that our prediction models perform equally well on each of these groups. And of course, fairness considerations, there are many aspects and dimensions to fairness considerations. And I'm just positing here that we want models to perform well across groups. And of course, understanding different notions of fairness is an important area of research that both folks in computer science as well as in related disciplines are thinking about. And I'm really excited about this because it's a way for us to talk to those communities. But here we focus specifically on trying to ensure that the accuracy of underrepresented groups is as high as for overrepresented groups, ideally without harming at all or minimally harming overall average accuracy across groups. And one additional challenge that we added in this setting was to not just focus on the performance in underrepresented groups, but also take into account the possibility that underrepresented groups might be disproportionately underrepresented in our data sets as we collect them, which we know is often the case in practice. And this challenge, this what's called subpopulation shift of subpopulations or groups being disproportionately underrepresented is an additional challenge. So this is a very challenging problem, and it's been studied for a few years in the machine learning community. And here the question is, how can we train models that exhibit high group robustness? And so I'm not going to go into the specific details of the prior construction, but I want to give you a high-level picture of what we try to achieve. Specifically, the goal is to achieve high accuracy on underrepresented groups without harming average accuracy at all or not harming it too much. So specifically what we want is if we have a continuum over here, on the x-axis here on the left, we have models that are not group robust. On the right, we have models that are group robust. What we want is we want to specify a domain-informed data-driven prior that places high probability density on models that have this desired property. So that when we optimize the model, taking into account this prior, the model favors or is primed towards those desirable solutions. And in this case, we, of course, again, need to specify a data-driven prior, which is just, again, the distribution of the model parameters conditioned on context data. And in this application setting, the context data contains information about which groups are underrepresented. So each image does not just come, for example, with a class, but also with corresponding group information. Now, let's take a look at how well this approach does. So over here on the left, you see 3 different data sets that are commonly used to study group robustness. These are the first 2 here, Waterbirds and Celeb A, are computer vision data sets, and multi-NLI is a language data set. And each of these data sets exhibits underrepresented groups as well as subpopulation shifts. So how well do standard methods do? So here we just have kind of a very highly trained and polished expected risk minimization method. So a neural network that is trained without, with standard mechanisms that improve generalization. But this is not kind of a fancy method. This is just using our standard techniques that we know work well to achieve high average performance. And what you see here, the larger numbers are the worst group accuracy, which is the accuracy of the model on the group that it performs least well on. These are typically the most underrepresented groups. And in parentheses, you see the average accuracies. And as you can see, there's a huge drop in accuracy, in the average accuracy compared to the accuracy on underrepresented groups, right? So in the first case over here, we have like roughly 20 percentage point decrease. Here we have roughly a 40 percentage point decrease. And here we have another like 15 to 20 percentage point decrease, right? So these are really, I think, unacceptable degradations in performance on these groups. So what happens if we use a data-driven prior with a little bit of group information? So I should say, this method does not use any group information. So what we see here is that by using a group-aware prior, we see massive improvements in performance, 20%, 30%, and another 12% over here in the worst group accuracy without harming the average accuracy very much. And you see that there is some decrease in the average accuracy, but this decrease is very consistent with other methods in the field, while we get this very significant improvement in the worst group accuracy. Now, you might point out that this is absolutely unfair comparison, right? Because expected risk minimization does not use any group information. Now, let's take a look at distributionally robust optimization, which is a well-established method in the field, still continues to be close to the state of the art, and uses a lot of group information. In this case, we see that group-aware priors use a mechanism that still allows us to achieve improvements, albeit small improvements, in the worst group accuracy. I should point out all these improvements are statistically significant. And over here, you see that even the average accuracy improves a little bit. But the important thing here is that our method, group-aware priors, only uses minimal group information. Specifically, it uses about 10% as much group information than distributionally robust optimization does. And this is important because group information is really expensive to gather, right? You actually need human labelers in order to take an image that might already have class labels that may have been acquired using human labelers or automatic methods, and then actually add group information to your data set. So obtaining group information is expensive. So being able to do this as well or better using only minimal amount of group information is incredibly important, because the kinds of models or the kinds of models that would be models deployed by tech companies, typically often private actors, not exclusively, of course. But in those cases, there are financial pressures. We want to make sure that these models work as well as possible with as little group information as we can. And of course, there's a very interesting and important socio-technical aspect here, because we face a trade-off between cost of obtaining group information as well as performance and equity in these models, which I think is a very interesting and important aspect here. And this is where sort of governance and policy questions come into play. I just briefly want to mention a few other applications that I've explored using data-driven priors. These include safer predictive drug discovery, as well as clinical decision-making. A follow-up to this work is currently under review at Nature Communications. We've looked at accurate and reliable semantic shift detection, essentially trying to use data-driven priors in order to raise an alarm when there is a semantic shift in the data. We've applied this to we've done this with computer vision and language models, so with great success. And we also looked at continual learning, which is the process of continual learning from new data, but assuming that we may not be able to continue having access to data that was previously observed. Continual learning often faces a challenge called catastrophic forgetting, where previously learned tasks being forgotten over time. We're able to construct a data-driven prior that mitigates catastrophic forgetting to a significant extent. So in summary, prior construction provides us with a blueprint of finding new training objectives that can actually help us improve trustworthiness of neural networks. And specifically, data-driven priors can improve the uncertainty quantification of neural networks under distribution shifts, which I believe is one of the most important practical settings, because we want to make sure that models don't fail unexpectedly in those settings. And lastly, data-driven priors can be used to improve group robustness. Okay, so with that, I want to talk briefly about some of my work on using probabilistic models to interpret pre-trained model representations. And as you all know, pre-trained model representations have been used to revolutionize much of machine learning. One example of a pre-trained model representation, one of many, of course, is CLIP, which stands for contrastive language image pre-training. CLIP is the backbone of most many vision language models deployed in practice and used in research. There are many applications of pre-trained vision language models in practice. Many of these are safety critical, for example, medical imaging, remote sensing, with the national security considerations, as well as robotics, where, of course, machine learning models are used to interact with their environment. So all of these are safety critical settings, really kind of leading us to the question, given that we deploy these models across a wide range of settings already, how can we make vision language model representations more interpretable? How can we understand whether vision language models really understand concepts that they're being asked to work with in practice? And one approach to do this could be a well-established approach like attribution maps, for example. Attribution maps have been used to explain model predictions. So for example, in classification settings. So for example, here we have an image of a cat and a dog. And if we have a model classifier trained on cats and dogs, we might have, we can use existing methods to obtain attribution maps that tell us which part of the image the model thinks is most related to the concept cat, and which part of the image is most related to the concept dog. And you see this works fairly well in this example. Now, the problem is that attribution methods, attribution maps that have been successful in the past tend to require labeled data in order to do so. So here, I said this was a classifier. So how can we use this idea of attribution maps in vision language models? Specifically, is it possible to create good attribution maps for vision language model representations without us having access to labels? And the answer is yes, because instead of using labels, we would be using the other modality. And so, sorry, let me just close this. So we've developed a method that we call the multimodal information bottleneck, or M2IB, that is designed to do exactly that. And specifically, we try to investigate whether a model understands a given concept. For example, we could ask whether a given vision language model understands the concept of a bear. So the way we can do this with this approach is to take a vision language model, which consists of an image encoder and a text encoder, and feed each encoder with different inputs based on their modality. So for example, we have an image of a bear. We feed that image into the image encoder, and into the language encoder, we use a description that contains some reference to this concept that we're trying to investigate. Now, once we've done this, we have these two encodings, and we slightly change them, which is by the way we do this is by adding a bottleneck into one of these two encoders. In this case, we add it into the image encoder, and in practice, this bottleneck is a mask, and we want to find a way to find a mask that allows us to investigate whether the vision language model is able to associate this text input with the correct parts of the image, right? Much like we did in the attribution map before. So how can we find a correct mask that does this? The way we do this is by having an objective that is optimized with respect to the parameters of this mask that involves maximizing the cosine similarity between these two encodings, while at the same time having a compression objective that tries to maximize the KL divergence between the distribution over this mask embedding and some uninformative prior. So these two objectives pull into two different directions. And in fact, this works very well in practice. And the reason why it does is because this objective tries to uses this KL term as a regularizer in order not to overfit, while at the same time trying to align these two representations through the mask so that the mask can focus on the part of the image, in this case, that is most relevant. And in fact, optimization of these model parameters theta over here corresponds to approximate Bayesian inference. So here we have a nice connection to probabilistic modeling. But of course, images of bears I think are cute, but they might not be kind of the most important application. Instead, given that vision language models have been deployed in settings such as medical imaging, we might want to ask whether vision language model representations in medical imaging settings are meaningfully interpretable. And so the setting that we looked at is chest X-rays, because of course, chest X-rays have been explored in computer vision for many years now. We have seen significant successes here, and vision language models have been deployed in order to perform classification tasks in vision from X-ray images with corresponding text descriptions. So what you see in this image is a chest X-ray with a text description of the medical condition that is present in these patients, and that can be seen in these images. And you see these bounding boxes focusing on the part of the image that exhibits signs of the medical condition shown in the text. Now, we were not the first people to try to come up with attribution maps for vision language models. Let's take a look at kind of how well other methods did. And some of these are more recent methods. Other methods are a little bit older but well established, like GraphCam and saliency maps. And what you can see here are the heat maps that indicate, according to each of these methods, what the vision language model thinks is the part of the image that is most related to the text description. Don't focus on the highlighting in the text for now. We can talk about that later if we have time. I want you to just focus on the heat maps in the images. As you can see here, the heat maps are all over the place, right? Most methods show different heat maps, and most of the methods don't actually have heat maps that place the highest emphasis on the area that is shown in the bounding boxes, right? So this is pretty bad, right? Because ultimately what this means is that it's one of two things. Either vision language model just doesn't understand the concept that is expressed in text and can't really match the text to the images, or these methods are imperfect. Well, we investigated this and used our own approach to see how well we would be able to do with the information bottleneck approach that I showed you on the previous slide. And these are results, the results with our method. And you see here that our method very nicely pinpoints the areas over here that are shown in the bounding boxes, and it does so significantly better than all of the other methods. So this tells us two things. First of all, it appears that all of these other methods are just insufficient in providing good attribution maps. In fact, given that our method is able to actually find the attribution correctly, this also indicates that the vision language model does, quote unquote, understand the concept that is expressed in text. Now, one thing that I want to highlight that I think is super cool about this result is that we looked at this and we saw, this is, by the way, just one of many results in the paper. We have many randomly sampled attribution maps. We try to be very forthright about, when the model does well and when it doesn't. This is a pretty representative example. There's some examples where our model is able to give like a even better picture, and some where it gives a slightly worse picture. But what's really exciting here is that I thought that the result in the bottom right was not terribly good, right? The bounding box is pretty large, and the model really focuses on this small part to describe local consolidation in the left mid lung, which is, some liquid in the left lung. And these images are flipped. So, left means kind of it's actually on the right in the image. And I spoke to some colleagues who are physicians and asked them about this, and they actually told me that, interestingly, these bounding boxes were pretty imperfect. So we looked at a few different images, and this is one example where the bounding box was imperfect, and the bottom right area over here actually shows the heart and doesn't focus on the consolidation, which is really shown in this area of the image. So this tells us something very interesting, which is that not only can we use this method in order to investigate whether a vision language model understands a given concept, but in this case actually did even better than the human labeling, which in chest X-ray studies is known to be fairly noisy. But beyond that, we might be interested in having more than just vision language modalities in order to investigate whether models are able to understand concepts across modalities. And so we used the model that was released by Meta called ImageBind. that that provided embeddings for 7 different modalities. And specifically, just make sure my sound is turned up. Let me just play this. All right, so this was for those of you listening on Zoom, if you weren't able to hear this, this is a meowing of a cat. And we asked whether a vision language model is able to understand this meowing as corresponding to a cat by taking a look at a corresponding image of a cat and a dog and a sentence that says a cat is meowing or a dog is barking. And in fact, our attribution method was able to pinpoint cats fairly well, as you can see in this image, as well as in this highlighted text over here, which I think is pretty exciting. And I think that this is the way I think about this is that this is the first step in really understanding vision language model representations more deeply, for example, using probabilistic methods. So in summary, we can interpret vision language models using multi-model information bottleneck attribution, the method that I described. I think excitingly, this method corresponds to approximate Bayesian inference. And we can even extend this approach to arbitrary combinations of modalities like I showed in the previous slide. So with that, I want to wrap up. And before I briefly talk about some future directions, I talked about how we can improve robustness and transparency in neural networks using probabilistic methods. I talked about some of these works that were published at various machine learning conferences. I've also done work on drug discovery and using probabilistic methods for reliability and safety in that setting. And I've also focused on using probabilistic models in order to uncover model assumptions, preventing model failures, and to construct models more transparently. In future directions, I'm particularly excited about various aspects of generative models and foundation models. One area that I'm particularly excited about is steering foundation models towards trustworthy behaviors, much like I showed in the first part of this talk. And of course, we know it's difficult to align foundation models with human intent and to make them trustworthy. This is especially true under distribution shifts. So my goal in future work is to use large pre-trained models together with trustworthy priors and compression methods in order to align foundation models with human preferences more effectively. I'm also very interested in continuing my work on uncertainty quantification. And this is based on, of course, the observation that generative large language models don't actually know what they don't know. This is an area that is particularly interesting, I think, in general, but especially if we're thinking about distribution shifts. So, language models being deployed in settings that the training model, that the training data might not be as representative of. And here too, I've worked with Google to make a first, dent in this direction, and I'm very excited to continue working on this research direction. And beyond looking at uncertainty quantification under distribution shifts, I'm also very interested in paradigms of model safety. One such paradigm is scalable oversight in large language models, which involves using model oversight for uncertainty evaluation, especially in unstructured and open-ended domains. So here we use a human and a possibly not frontier large language model in order to oversee a more capable large language model that might be deployed in safety critical domains. I've been involved in an initiative called the Open Metatron Initiative, which creates and for which I'm the safety team lead. And the goal of this initiative is to create large language models that can be deployed in resource-constrained settings across Africa to provide reliable medical advice. And in those settings, we need oversight mechanisms that can be automated and that are reliable. And part of this effort is supported by a CSAT Foundational Research Grant, which supports this research. As a final note, I've been working on AI policy, law, and regulation. I've authored a number of papers on that area. This work has been referenced across the White House, for example, in the Office for Science and Technology Policy. I've given talks on this at the OECD, as well as at the Responsible AI group at the DoD. And of course, this is part of a bigger shift push by the United States government as part of their executive order last year to create trustworthy artificial intelligence. And more recently, I've been involved as a member of the US AI Safety Institute Consortium, where we tried to bring together technical experts in the technical, non-technical experts in the creation of the US AI Safety institute, and I really believe that research on topics around trustworthiness should really involve AI policy, methods, and evaluation, and all of these different approaches should go hand in hand and form one another. So with that, we're back where we started, which is that machine learning models often fail when exposed to unexpected conditions upon deployment. Talk to you about a few different examples where this is the case. And I've talked to you about some of my work that I've done to successfully create more trustworthy machine learning models by improving robustness and transparency in these safety critical settings. With that, I thank you and want to highlight my advisors and collaborators who I've been very fortunate to work with. And I'd be happy to take questions. Thank you so much.
Great, so we can take questions in the room, on Zoom also. We can take questions if you're on Zoom and have questions. You can either use your raise hand feature and we can call on you. You can type into the chat. You can unmute and say something. I know we are well over the scheduled time, but I do want to give, if there's a couple of questions people would like to ask now.
I'll also pull up the chat.
It's mostly me. Thanks.
Yeah.
It's really interesting, great art. What you've done. I wonder what your experience to with policymakers.
I love that question. So for folks on Zoom, Lucy asked about my experience working with non-technical folks in the policy space, for example, and my experience doing that. So I've been involved in a few different efforts. I worked with the OECD to where I helped draft a report on classifying different AI systems to give policymakers kind of an easy to use guide that can allow them to determine kind of the risk level of different systems. And I've worked with folks at Center for Security and Emerging Technology. Like I said before, I've issued a few papers on key concepts in AI safety with my colleague Helen Toner at CSED. And I know that these papers have been used widely kind of across government agencies, et cetera. And I've had a very positive experience interacting with policy folks. I feel very passionate about communicating some of these ideas to non-technical audiences. And I think, that being said, of course, it's not easy, right? We do sometimes speak different languages. We have different, to some extent, different things that we understand and are trying to optimize for in our respective fields. And it's really kind of my goal to try to bridge those different communities. And I think, I would be lying to say that it's not challenging sometimes because of different incentives. But I am very excited that this is just that there's a more general push to ensure that machine learning systems are deployed in a safe way. I'm particularly excited about the effort that is done as part of the AI safety institutes, which have significant, have technical personnel. This is true, especially in the UK, where the AI Safety Institute already exists and is producing work. In the US, kind of the AI Safety Institute is sort of in the process of being set up. But I think that those are really good platforms that really ensure that the technical folks who work on problems that are most aligned with what we need in policy. And in terms of my own research interests in policy, I view my own work on technical AI governance as really trying to think about what kinds of technical insights do we need in order to do effective policy, and how can policy complement the technical insights that we have? Because of course, we don't have mathematical guarantees for machine learning models. It's an active area of research that I'm pursuing to try to get mathematical guarantees for large language models, for example, and I published a paper on this at ICML this year. But at the same time, we are not quite there yet. And I think that the way I think about policy is that we can use regulatory as well as legal mechanisms in order to complement kind of the lack in the technical realm that we see at the moment. I feel like this is something that everyone, technical, non-technical folks who are working on this is on board with and excited about. Thank you. Any other questions?
Seeing none, thank you again.
Thank you so much.
And thank you all for putting up with our disruptions.
Thank you, everyone on Zoom. Thank you.